My name is Manish. I work at a company called ClickHouse, and today we're going to be talking about Kubernetes, stateful sets, migrations, and so forth. So, quick introduction about me. I manage the auto-scaling team at ClickHouse. Jayme, you want to introduce yourself?
Yes, I'm Jayme. I work in the auto-scaling team. I'm one of the software engineers in that team. Yeah.
Yeah. So we mostly do like vertical scaling, horizontal scaling, idling, scaling to zero of the database, and we're going to go into like the details of why that's relevant in the context of the migration that we're talking about. So this is the agenda. We're going to talk about auto-scaling in general and how it works inside ClickHouse. We're going to talk about a new approach to auto-scaling that we've been developing over the past couple of years, which what we like to call make before break. We're going to talk about what the migration is. So the make before break stuff is basically the context for the migration that we had to do, which contains of two parts, orchestration and execution. And then we're going to go into some of the challenges that we faced during the migration. So first of all, ClickHouse. I don't know, has anyone here heard of ClickHouse before? Oh, lots of hands. That's nice. Yeah, so for those who haven't, it's an open source, column-oriented distributed database. It's an OLAP database written in C++, known for its performance, analytical workloads. I guess most people know, but yeah, if you haven't tried it out yet, and if you're interested in like high-performance databases, so please check it out. So ClickHouse Cloud is our managed offering of ClickHouse. The company has been around for about 3+ years now. We provide like a serverless, fully managed experience. You can do like idling, scaling to zero. There's a separation of compute and storage, which is not available in the open source offering. And this is how it looks like, right? So the storage is disaggregated from the compute, and we basically use Kubernetes. So all the server replicas are deployed as Kubernetes pods that have PVCs attached to them. The PVCs contain metadata, so not any actual data. They're basically just metadata pointing to the data that lives on S3 or any other object storage, and we're available on all three cloud providers. And for those of you who don't want to kind of run inside the fully managed offering, but just want to have the same experience inside your own virtual, virtual network, there's a BYOC offering that offers something very similar. And because like I mentioned, we run on Kubernetes, this is the very high-level architecture of what it looks like. So we have an operator, we wrote our own Kubernetes operator that manages those server pods. And of course, because it's a stateful service, like a database, not a web server, we use StatefulSets to manage those pods. And we have like PVCs attached to that, which have the metadata. And the main resource here is the ClickHouse cluster custom resource. So why am I talking about auto-scaling? That's going to become relevant, but this whole problem started when we kind of started to do vertical scaling. And just to kind of set up the problem here, I'm going to give a high-level overview of what auto-scaling looks like inside ClickHouse Cloud and in Kubernetes autoscalers in general. So we have something called an autoscaler. You have a pod that you need to resize, right? Maybe it's got 10 gigs of memory, you want to give it 20 gigs of memory. And that resize operation is only going to happen once the autoscaler does something which is called a pod eviction. It's going to kick a pod, which is going to get deleted. And then the controller, it could be any kind of a controller. In this case, it's going to be the stateful set controller, is going to resubmit that pod, and that resubmission will resize the pod. Zooming in, how does that resizing actually happen? So when the pod eviction happens, here you can see and the controller resubmits the pod spec. That pod spec is getting intercepted by what we call a mutating webhook, which is like an admissions controller here. So this webhook is going to intercept the payload of that pod and then basically take the input from anything else. So in this case, you can see on the very left, we have like recommendations or the user's defined limits. So for example, I'm a user of the cluster, and I want to define the limit that, hey, instead of a 20 gig memory, I need 30 gigs or some other number. And that gets read into the mutating webhook, which will just mutate the spec and then resubmit it. And when the pod comes up, it's going to come up with a bigger size. So yeah, vertical scaling, this is what it's about, right? We want to go from some size could be CPU resources, could be memory resources, so some resource limit, which are starting, and then a target resource limit. And this is effectively what it looks like. This is what we want when we talk about vertically scaling a service. The problem with vertical scaling is in that by default, when you do vertical scaling inside Kubernetes, it's the model that we are calling the break first model, it's kind of implicit that when you have like a disruption budget, in this case we have like a max unavailable equals 1, and you always want a disruption budget because otherwise you'll just have like complete unavailability for temporary duration, because remember, we are doing pod evictions, right? So every time you evict a pod, that pod becomes unavailable. It can't take any queries. While respecting the disruption budget, you want to do queries, and then effectively what this comes down to is a rolling restart of all the replicas that you have inside your cluster. And this is a very slow and painful process because, remember, there's queries running on these replicas. There could be backups. There could be long-running queries. You want to do like a graceful termination. You want to wait maybe, I don't know, 1 hour or some amount of time before you actually decide that the process is ready to safely terminate and then come up again. And the startup can also take some time, depending on how heavy a workload the cluster is running. So rolling restarts, they're slow. The other problem that happens with break first scaling is it causes a lot of pressure. So if you think about it, like, and you have like a workload running, and it suddenly requires more resources, which means more memory, more CPU. That's probably the worst time for you to actually take away a replica, right? So in this case, we can see the third replica is getting restarted, but the first two, of course, the workload probably hasn't changed. You should assume the worst, that the customer workload is probably just increasing, and that increased pressure, as well as the pressure from the third replica, is going to get redistributed to the other two. And when that happens, in the worst case, the remaining replicas can also just crumble under the pressure. So this is also a problem with this sort of a rolling restart model of scaling. So just to summarize, break first scaling is slow, it's disruptive, it puts pressure. And actually inside our cloud, what we've done is we've added like some sort of an extra overhead of memory and CPU resources just to combat that extra pressure that happens while the pod is undergoing the restart. And so to combat this, we started thinking about what we call the make before break scaling model. And here the idea is also pretty simple, right? So instead of doing a rolling restart and causing pod evictions, just add more replicas and then take away the old replicas, right? So in this case, we can see we added the 32 gig replicas and then immediately broke the 16 gig replicas. Why is this better? It's better because now you're not bounded by any sort of a termination. As soon as you add replicas, you immediately have that capacity available to actually contribute to the scaling. So when you need capacity, all you need to do is just add replicas and then take away the old ones. But you don't even need to take away the old ones for the customer's workload to start working. It's immediately available to you. So yeah, it's fast, it's not disruptive. You kind of also immediately got rid of the problem of the pressure during restarts. And if you do this mode of scaling, you immediately get rid of the extra overhead. So your allocation and your utilization can be very close to each other, which means your customers are not paying any extra for that overhead. This sounds like conceptually a very simple idea, but Kubernetes makes it surprisingly difficult to implement this idea, and I'm going to talk about that why. So a stateful set in Kubernetes, when it's actually undergoing scaling and adding and removing replicas, it's using an ordinal-based approach. So we have like stateful sets starting from ordinal 0, 1, 2. And if we think about this in a make before break approach, when we go to replicas, when we add replicas, which is the make part of our system, we can just do 3, 4, 5, and that's perfectly fine. But the minute we actually want to break replicas, we tell the stateful set, hey, please give me 3 replicas. It's going to go the other direction. So the arrow below, which is scaling in, it's going to remove replicas 3, 4, and 5, which is not what you want to do. You want to remove replicas 0, 1, and 2 in this diagram. And Kubernetes stateful sets don't allow you to do this. There is one hacky way of kind of bypassing this limitation, which is in this Kubernetes enhancement proposal, which is the start ordinal. So you can just always for a stateful set, say, hey, instead of starting your replica ordinals at 0, start it at 1, and then start it at 2, and so on. But this kind of works, so it technically gives you the make before break mode of operating, but it has a problem. The problem is that maybe replica 0 is running a backup, and you don't want to break it. Maybe replica 2 is running a query, you don't want to break it. You only want to break replica 1, which is currently kind of not doing too much, it's not that busy. It's something that's eligible to be broken, but you can't do that because the start ordinal, you can only break the replica 0. So it's only going to shift sequentially from left to right. So it's not flexible enough. So the problem is we want to break arbitrary pods, and that's something that's not available to you. We looked at some third-party controllers. So there's OpenCruise clone sets. There's advanced stateful sets. Those projects by themselves were not something we wanted to use, but we picked up a key idea from them, which was the idea of having delete slots. And this idea is pretty simple as well. You can just add a delete slot annotation, and then just your controller is going to read that delete slot and then just pick up and remove that replica arbitrarily. You're going to have to do some customization, but it's doable. So we wanted to use delete slots, but of course, delete slots are not an idea that is available inside the stateful sets in general. So we were kind of already approaching the point where we needed to make our own custom solution, which should look like a stateful set, right? Stable identity. We wanted to get rid of ordinals because of the problems I described before. And then have all the support of PVCs, respect the disruption budget. Topology spread constraints also became important, and we're going to talk about why. And so the approach to that was pretty simple. Instead of using a single stateful set, we wanted to use like what we have been calling multi-STS approach, which is we still want to have the stateful set. The vanilla stateful set from Kubernetes is very powerful. We want to leverage it. But instead of having one of those, we can just have many of those running at the same time. And there's actually a very good benefits to this, which is the stateful set controller is still going to be around. So the operator, the ClickHouse operator, is the code base that we change most often, and we did not want to introduce a lot of bugs while we don't want to kind of break the pods by accidentally introducing a bug. So the stateful set controller serves as kind of a layer between us. So even if the operator is doing something weird, the stateful set controller keeps reconciling the pods, and your server pods are still kind of stable. And in terms of code refactoring, it's also pretty nice that instead of using one, you can use many of the same thing instead of using a custom object. So it saved us up a lot of refactoring as well. And this is what it looks like. So this was the before thing. Before we were using a single stateful set, which was managing all 3 pods. And afterwards, we just added a bunch of stateful sets, right? So this allowed us to just immediately do the make before break, or the MBB style of scaling, which is now you have these 3 stateful sets. You add a 4th one. This is the make step. And then you can just immediately break one. After there's going to be some synchronization, because remember, we're talking about a database here. We're talking about a multi-master asynchronous database that's taking inquiries. So there's going to be some catalog synchronization that's going to happen. And then we're going to just break this arbitrary replica. And that's it. And you do this 3 times, and or maybe you even do it in a single cycle. Instead of adding 1 replica, you just immediately add 3 replicas and then break the other 3. And then you're done. So why do we need migrations? Because we have a fleet of thousands of these single stateful set clusters. The customers are running their important workloads on them. We don't want to disrupt those workloads. But they still need to be migrated in order to leverage the faster, better way of scaling things. So hence this talk, which is about the migrations. And the first requirement of the migration was that we cannot have downtime. Why? Because we have other areas in which we needed to do other migrations, which are totally not relevant to this problem. But just as a product, we wanted to have like as minimum downtime as possible. No downtime would be perfect. There are going to be some sort of an orchestration requirements to this thing. It's not something you do in a single day. There's a lot of organizational overhead. You need to contact customers, all that stuff. You need visibility into this. Because this is the database operation, you're going to encounter strange issues while this is happening. Every time a customer, because customers are doing very strange things to the databases, so you're going to have like very unique issues. We're going to talk about those as well. And of course, because it's a migration, you should be able to roll it back. So no downtime via MBB. This is what it looks like, right? So a single stateful set managing 3 replicas. The funny thing here is even the migration itself is a make before break style of migration. So you make 3 extra stateful sets, and then you break, you do a sync, because now all these 6 replicas are kind of in synchronization. And then you break that first stateful set, which is managing the 3 pods. And at the end, you're just left with the 3 replicas. And this is kind of how you go from a single stateful set world to a multi-stateful set world without any downtime. So this was the approach which we wanted to orchestrate. The problem was, of course, that we did not want to kind of do this inside our own Kubernetes operator, because this is a one-time operation for a cluster. And after we are done with this, we need to kind of get rid of that code anyways. So we ended up writing our own custom migration controller. And we used a tool called Temporal. I don't know how many of you have heard of Temporal? Yeah, some people. So Temporal is like an orchestration tool that we use to basically schedule these migrations. So let's talk about Temporal first. So the workflows in Temporal are kind of, I'm not sure of the slide, but yeah, this is kind of the better slide to introduce Temporal. So we have, it's something called a durable execution framework. So think of it like a job engine or a workflow engine, only the state is durable in the sense that you actually don't need to do any database operations. You don't need to say, okay, now please insert all my data into this database and then read from it. All of that is done for you. You just define your inputs, you define your outputs, and then things are persisted for you, which is very nice. It gives you a lot of other features out of the box, like failure detection, retries, timeouts. Gives you scheduling capabilities, so if you want to use it as a glorified cron job, you can. It's very composable, so you can compose different steps together inside the workflow, and it's very scalable. So workflow, what's a workflow inside? So these are just two terminologies I'm going to throw at you, a workflow and an activity. We're going to talk about workflows first. Workflow is basically like your job spec, right? It's a DAG or like a sequence of steps that you want to execute. Each individual step is called an activity, and what it does, it's basically a retriable thing. The very nice thing that it gave me, because remember, these migrations are something we wanted to almost babysit. We wanted to handhold these migrations, but at the same time have some sort of an automation. So it's interruptible, right? So you can always be in a place where you send something happens which you don't want to happen, but send a signal to an on-call engineer, and then pause the job right there. And then once you've kind of verified the situation, either abort or continue, which is a signal that the human can send back. So that's possible with this kind of a framework. And it can also have like child workflow. So you can have like one workflow running on every individual cluster, but then have like a parent which is managing all those workflows at the same time. And like I said, it can run on a schedule. So activities is the second kind of piece of jargon that I'm going to throw at you, which is the unit of work that is happening inside these workflows. So any kind of an external interaction, be it with an API, with a database, or a Kubernetes controller, all that work is actually happening inside these activities. And the durable part is actually defined right here. So when you define your inputs and outputs of an activity, those get persisted, and you can chain them together. So for example, the output of the first activity can become the input of the second activity, and that's how like kind of data moves through this workflow. So this is a very simple example of an activity, right? So here we're just getting an instance, and that's very simple. So we've defined our input, just a parameter of the Go function, and the output is the second, like the return value. And there's nothing else I'm doing here. There's nothing fancy, right? I don't know if I can use the clicker here. So this part right here, which is where I'm executing the activity, that's it. It's just making an API call, and my inputs and outputs are persisted. And this is really important for one critical reason, which is after the migration was done, we wanted to kind of restore the cluster to the original state so that the customer has no idea of, like, nothing has changed from their perspective. Their configurations, their settings are all kind of resetted back to the original state. And this is what it looks like. So when you execute like a workflow, if you read from the bottom to the top, this is like as the time goes on, more and more activities are added, and these results are basically the outputs in the JSON. We were using the cloud service, so this gives us a really nice view of what's happening, allows us to do like a lot of very useful debugging as well. And yeah, this is basically a whole like a DAG with the timeline view of how the workflow was executing as we were doing these migrations. Like I mentioned, signals are really important for human intervention. So here, for example, we detected a drift in our configurations during the migration. We send a message to Slack. Some engineer is going to take a look at this, and then just going to send like a continue or an abort signal. And while that's happening, the workflow is basically just waiting for that approval or abort signal. I'm going to hand it over to Jayme to talk about the next part of the migration.
Cool. Thank you. So the first step of actually doing these migrations is organization and communication. Let me just attach this 1 second. So we need to make sure that communication to our customers about these migrations happens smoothly. If certain customers want to push back the migration, we need to track that. And our product team came up with a really nice tool to track this, a spreadsheet. So in general, in terms of organizing these migrations, one requirement that Manish mentioned earlier was we didn't want to have any downtime. We wanted inserts and queries from our customers to continue. But at the same time, we didn't want the customers to be able to do changes to their cluster that might affect our migration. So for example, we don't want them to change their auto-scaling settings in the middle of the migration, which could potentially cause issues. And it just simplified life for us if they didn't do this. So we built something called maintenance mode. I'll go a bit more into detail, specifically into maintenance mode in a minute. But other things, we want to send them emails. We want them to see in the UI that 2 weeks before the migration happens, we let them know a migration will be coming so they're not surprised. When the migration's actually happening, we let them know. And then we had some questions for ourselves. How do we want to actually run these migrations? Should we do them all at once, spread them out? We could have concerns like cloud capacity and other issues. And so we decided to migrate them in batches. And we also encountered some issues, which we'll go into, which made us spread it out even further. So let's start with maintenance mode. So I mentioned we wanted something where we could prevent customers from changing the cluster. So auto-scaling settings, as I said, other API requests customers can make, maybe backups. And we didn't want to bill customers. We wanted to ensure that billing was disabled. So we decided to implement something generic that we could use on our cloud product, and we've used it for several other migrations and features. So we made this maintenance mode. In this particular migration that I'm talking about, we used partial maintenance. So that's showing there that we allow inserts and queries. So from a usability perspective of the cluster, they can still insert and query just as normal. This just shows an example. It's a bit of an old UI from ClickHouse, because we started these migrations quite a while ago now. And it just shows the banners and UI showing that maintenance mode is coming on the cluster, that there's a migration happening, and so on. So now let's get into the meat of how we actually did this migration from an implementation perspective. So Manish mentioned we had a migration controller. I'm going to go a bit in depth in exactly how that looked. So yeah, migration controller. So I just wanted to say this was a test in general for ClickHouse in terms of dynamically scaling, adding replicas, syncing the catalog, and by catalog I mean the databases and tables, and making sure that all works correctly. So that's one aspect. Second aspect for ClickHouse is while we have an S3 on our cloud service, S3 storage, the data is in S3, but the metadata at the time was on local EBS volumes. And if that data was lost, we don't know which of those blobs on S3 relate to which tables and databases. So if we lose that, it's data loss for the customer. So these are two things that we definitely don't want to go wrong during a migration. We don't want catalog inconsistencies on the tables and databases, and we don't want data loss. From our own code, in terms of the operator, we wanted to test, does multi-STS actually work? So this migration, as Manish described, is an MBB, make before break event. So we are actually going to add replicas and remove them and see if that all works. In terms of our migration controller, we wanted something where we could add a label, and this migration controller would take over, perform the migration. We wanted something that could be reversible if we needed to. If something went wrong with the migration, we could undo it and go back to this single stateful set mode. And we wanted something where we could handle this intermediary state where you have multi-stateful set pods, single stateful set pods, and we don't want to add this complexity to our main operator. We wanted something that could handle this intermediary state, know about both worlds, and perform this migration without additional complexity that we'd have to cover all cases in our operator where this backwards compatibility would need to be placed. So this is just an overview of the migration. Maybe I can show here. We have a ClickHouse CR, so this is the custom resource that these controllers would be reconciling. Our ClickHouse operator is normally reconciling a single stateful set. This migration controller will create these multi-stateful sets. We have a mutex so that we don't have both controllers trying to reconcile the CR at the same time. So that gives you like a high-level overview. But more specifically, how we actually implemented this is our migration controller is actually a wrapper controller around our normal operator reconciler. And the reason we did this is because when our operator does a bunch of things that we need to do for ClickHouse when we create these multi-stateful set pods. For example, we need to create users. We need to sync the catalog, databases, and tables. And we didn't want to re-implement all that. So the first thing that the migration controller does is just call the operator reconcile and create all these things. But then at the same time, all that complexity I mentioned in terms of the backwards compatibility, orchestrating this migration, deleting these single stateful set pods, being able to be reversible, that complexity could live in this migration controller, and it could coordinate this and call the functions from the main operator as needed. So that's why I call it a wrapper controller, if that makes sense. I'll also mention here, we didn't end up needing to use this, but we did have a PVC snapshot controller that snapshotted these PVCs. As I mentioned, the data is on S3, but the part metadata was on EBS volumes. And so just in case, before we drop these single stateful sets forever, we snapshotted in case we needed that for a recovery. But we didn't end up needing it. So yeah, to summarize on the migration controller, it's a wrapper controller around our main operator. It handled all of this very specific coordination we needed for the migration, and it's backwards compatible. Now, everything's great, right? We have our migration controller, we have temporal to coordinate this, and of course, we wrote a bunch of tests, and this is, I'll be the first to say our test pyramid is not perfect, but we did a bunch of tests, unit tests, end-to-end tests. We have something called Stress House internally at ClickHouse that does stress testing, and so there'll be no bugs, right? We won't have any issues. Well, unfortunately, when we went to production, we found a bunch of issues, and I'm going to tell you a few of those issues in detail. So the first one is this make before break. So over here on the left, we have the single stateful set pods, and over here on the right, we have the multi-stateful set pods. And just for some context, at ClickHouse, along with multiple other services in the world, we want to have some zone balance, and we want to make sure that we have a nice balance of availability zones from the cloud provider. So here we've got zones A and B, and here we've got 2 replicas with zone C. So this is a completely valid zone topology, and we want to maintain this max skew of 1. So we don't want to have a case where we have too many replicas in one particular zone. In case that zone goes down, then you have a problem, right? The problem with this is if you're using the Kubernetes pod topology spread, and then we, as you know, we remove the old replicas, these ones over here, at the end we end up with 2 replicas in zone C, which is now a problem, right? It's an invalid topology. If C goes down from the cloud provider, we have unavailability for our customer. So that's quite bad, right? Another example of this, also with regard to zones, we have a feature called idling. So clusters scale down if they're not used by a customer. And when we unidle those clusters, we might also do an MBB operation or a horizontal scale out. And before those PVCs are scheduled, the Kubernetes scheduler doesn't know what zone those PVCs could be in. So it could add a new replica. So over here we have a new replica in a zone that conflicts with an existing zone of a replica in the cluster and gives us an invalid topology. So we ended up deciding to implement something we call zone pinning in our operator. So we control the zones. We control it during horizontal scale, ins and outs. We control it through MBB operations. And there is a feature in Kubernetes now called match label sets where you could implement it that way. But at the time, it wasn't available. So we decided just to move this logic into our operator. So this is now, we're moving into ClickHouse-specific issues. So you're adding replicas, you're syncing the catalog, database, and tables, and you're removing replicas. And you can run into all kinds of issues doing that. And so the first issue was ClickHouse has something called an on-cluster DDL queue. So if someone, for example, creates a database or creates a table on cluster, it goes into this queue. And at the time of running that query, it records the host name of each replica that was active in the cluster at that specific time. Now, when we drop replicas from the cluster, they no longer exist. And ClickHouse was trying to resolve those DNS names and failing if there was any queries in the queue. So this was something where ClickHouse wasn't great at adaptively adding and removing replicas. We ended up fixing this in ClickHouse as part of this migration. Along similar lines, we had problems with external table engines. So specifically in ClickHouse, you can have an external data source, think something like Postgres or RabbitMQ, and you have a table in ClickHouse that refers to this external data source. Now, it makes a lot of sense that when you create this table, ClickHouse should check that this external data source is accessible and that it exists, and if it doesn't, it throws an error. The problem here is when you add, for example, a new replica during this make cycle, when you're adding 3 new replicas, it shouldn't actually check that because it's completely valid that you've turned off that external system temporarily. You're not actually creating the table, you're just adding a new replica. And when it tried to run those create table statements, it failed. So to fix this, ClickHouse now has a secondary attach where when a new replica is added, it's not treating it as the first time it's creating those tables, but rather attaching it tables that already exist and doesn't throw those errors. Again, along similar lines, ClickHouse has a feature that's very popular called materialized views, where you have a source table and a destination table, and you might have some trigger that causes a computation at insert time to do some aggregation on some data from that source table and inserts it into a destination table. And it's completely valid to delete that source table at some point, but still have the materialized view, the destination table. But when adding replicas, we were hitting a similar issue as the external table engines, where we get an error that that source table should exist. Again, this is just something that the maturity of ClickHouse in terms of adding and removing replicas improved through these migrations. Unbreakable replicas. Just one second. So Manish mentioned we have this sync stage where we want to sync all the part metadata. So we've added a replica, and before we remove the old replicas, we want to ensure everything's synced. So let's start with a situation where we have 6 replicas, we're receiving customer traffic, everything is great. And on the left side, we've got S1 to S3, which is the single stateful set clusters. Now, those clusters are being removed, they're being dropped, and that process involves first removing them from the load balancer so they no longer receive any customer traffic. So that's the first step. And we do that so that when we sync the part metadata, there's no new inserts coming in from a customer, right? Now, we run a command called system sync replica lightweight. For example, here we're doing it on M2, one of the multi-stateful set pods. And what we want is to sync all the part metadata from all the other pods onto M2. So we want to make sure that everything's synced and we can safely drop S1 to S3. Now the issue is, in this example, both M1 and M3, the new pods, are receiving traffic. And ClickHouse is waiting for them to sync as well. Now if a customer's just consistently inserting into ClickHouse and there's always traffic, it'll never sync, or at least it will time out very frequently. So we solved this by adding a from modifier into ClickHouse for this query for system sync replica lightweight. So you can specify I want to sync from these specific replicas, in this case S1 to S3. So you can do system sync replica lightweight, S1, S2, S3. And then we're only waiting for these ones, which, as I said at the beginning, no longer receiving customer traffic, will be very quick to sync. So consistency of the DDL queue that I mentioned earlier, where the hostname issue popped up, we had a consistency issue where, because we're recording the host name of the replicas at the time the query is made, so you make a drop database query or a create database query, and we record the host names that exist at that moment, if this doesn't actually execute on one of the replicas that we're going to drop, then that query will just never execute anywhere, right? So we've got our new pods, the multi-stateful set pods. They don't have that host name in this list. It's never going to execute on them. And so how did we solve this? In our operator, we make sure that the queue is drained before we drop replicas. There is a better solution coming in our cloud product, which is an S3-based shared catalog, so that there isn't these replica local issues. So system tables is something common in many databases. ClickHouse has system tables. You can use them for introspection of ClickHouse. You can look at, for example, the query log or the metric log and see a lot of information about what's happening inside the database. Now, these are replica local. And as you can imagine, when you're doing this make before break operation, you're going to lose these system tables when clusters are dropped. And that's not great because it's useful to investigate these for data loss incidents. It's useful to look at it for historic metrics, for example, how queries performed in terms of memory and CPU and other dimensions. So for these migrations, we decided on a stopgap solution where we just copied this information during the sync phase. So in addition to system sync replica lightweight, to sync the part metadata, we also copied all of these system tables over. Now this wasn't great because if customers had huge system tables, many terabytes, we have to wait and copy all of that data. So this prompted the design of a new disk type in ClickHouse. There's a PR linked here, or an issue linked here. There's a PR now that's been merged. It's called S3 plain writable, and this is a disk that allows ClickHouse to attach those tables. So when we scale in replicas, for example, the single stateful set replicas and the examples we've shown, we would just attach those system tables without having to copy the data. So yeah, to close out this, I just wanted to mention that besides the technical challenges that we ran into that you see there, which caused some stop-starts, there's also the aspect that many customers don't want to do migrations for one reason or another. They're very scared of migrating their database if they have critical workloads. They might have some very important event that they rely on that database for. And so this causes issues where you have this huge long tail of customers who don't want to migrate. It gets pushed forward. And so this process took over 1 year to migrate a couple thousand clusters. And some migrations got stuck from those issues that I described for up to a week. So we had the situation where we had the single stateful set and multi-stateful set pods both existing for up to a week. And I think migrations in a database, for example, are super important because if you have data loss, it affects the product's reputation, right? So you need to take these seriously. Yeah. If anyone's got any questions, we can take those now. We're also at our booth tomorrow, so come and speak to us if you want to speak. We're hiring. We've got the Slack community if you want to join.
Hi. Thanks for the talk. Tell me if I get this correctly from an architectural perspective or level. This is the migration here in order to be able to do vertical scaling. You are mutating your cluster. Have you considered instead creating a copy of the cluster, assuming you're running in cloud, so you can have the shifting resources, creating another cluster, and then you can, for example, snapshot it. I understand that the data is in S3, so even snapshot from S3 instead of your EBSs, and then maybe do logical replication. And this also allows you, or the customer, if you expose it to the customer, to do like A/B testing to make sure that the new cluster is suited to the needs. So it allows you maybe less of technical issues with the mutation, but also some added benefits like A/B testing or horizontal scaling, having like more read throughput, etc.
Yeah, so I think firstly, we did consider this, and in fact, we had a migration from the table engine of replicated merge tree to shared merge tree that was very much in this manner with taking a backup, snapshot, and then restoring into a new cluster. But a big motivation for the way we did the migrations is that this was a test of make before break, where we are adding replicas to ClickHouse and then removing replicas from ClickHouse, which is how our scaling will work going forward. And by testing this and finding those issues I described, it makes ClickHouse more elastic at scaling. So being able to add replicas and remove them quickly, finding those issues was really valuable to us so that now we can, for example, do those scaling events and not hit this DNS issue or this external table engine issue. Because we would have hit those when we actually enabled this form of scaling otherwise. So that was a reason that we did it the way we did.
Another issue would be that if we were to create a new cluster, we would need a way to kind of reroute the queries. Remember, this is a live migration, right? So when you're adding replicas to the same cluster, when the new TCP connections are made, we didn't mention it here, but we actually temporarily disabled the external connectivity from the old replicas that we are about to remove. So queries can still go to the new replicas. With a new cluster, instead of just adding replicas to the old one, we would need to find some way where all these two clusters can technically be part of the same ClickHouse cluster. And I don't think we do that because we have namespace-based isolation. So we would have to find a way around that as well. I don't know if you think about that.
Anyone else got anything?
All right. Cool. Thank you for attending the talk.
Thank you.